As we know, time is an important concept in physics and in life. To measure time, we need devices that can track the changes of a certain quantity according to specific rules. These devices are called clocks. Throughout history, humans have used various types of clocks, from hourglasses, water clocks, sundials to mechanical, electronic, and atomic clocks. Among these clocks, atomic clocks are the most precise, capable of measuring time with very small errors. In a recent breakthrough study, a group of physicists announced one of the highest performing atomic clocks ever built. This clock can measure time so precisely that it only deviates by 1 second every 300 billion years, aiding in the study of physical phenomena such as gravitational waves. Simone Cohn-Kowich, a physics professor at the University of Wisconsin-Madison and the lead author of the study, said, "Optical lattice clocks have been the best clocks in the world, and we have improved their performance to a new level. We not only enhanced their performance but also developed new applications based on this high performance." Atomic clocks are clocks based on the oscillation of atomic frequencies, typically cesium or rubidium atoms, allowing for high-precision time measurement. S application is NASA. Atomic clocks work by tracking the energy levels of electrons. The University of Wisconsin-Madison explains, when an electron moves from one energy level to another, it emits or absorbs light of a specific frequency that is the same for all atoms of the same element. Optical atomic clocks use lasers with frequencies matching this to keep time and require very sophisticated lasers for precise time measurement. The new study used a clock that separates strontium atoms into a row in a vacuum chamber. The research team used a not-so-great laser, as Cohn-Kowich called it, but still achieved results close to the world record for precision. If a laser is shown on only one clock, electrons with the same atomic number will oscillate for about 0.1 seconds. But when shown on two clocks simultaneously, the electrons oscillate for 26 seconds. Our laser would normally reduce the performance of these clocks, Cohn-Kowich said. But because the two clocks are in the same environment and affected by the same laser, the laser's effect is cancelled out. Then, the team precisely measured the difference between the two clocks. As atoms in different environments tick at different rates due to changes in magnetic fields or gravity, the team repeated this experiment over 1,000 times to measure the differences and found that the precision of the measurement increased over time. Ultimately, the researchers determined that the difference in ticking rates between the two atomic clocks corresponds to them differing by only 1 second every 300 billion years, a world record for precision in time measurement between two spatially separated clocks, according to the University of Wisconsin-Madison. In the same issue of Nature, another unrelated study reported a frequency difference between the top and bottom of a dispersed atomic cloud, about 10 times higher than that of the University of Wisconsin-Madison group. This study, by Georgila, formerly of the Institute for Astrophysics in the Laboratory, a research institute in Colorado, set the world record for the most precise frequency difference. The University of Wisconsin-Madison group came in second. Cohn-Kowich said, "It's interesting that we could achieve performance nearly equal to the Zilla group even though we used this is very important for practical applications, where our laser is very similar to what you could take outside." So how did Zilla measure the frequency difference between the top and bottom of a dispersed atomic cloud? According to Einstein's theory of general relativity, time flows slower in places with stronger gravity. This means that atomic clocks, the most precise time measuring devices today, tick at different rates when at different altitudes. This effect has been verified many times by comparing atomic clocks at different positions in the gravitational field. However, measuring the frequency difference between atomic clocks at very short distances is a major challenge for researchers from Zilla, a research institute in Colorado, announced results measuring the frequency difference between the top and bottom of a dispersed atomic cloud with unprecedented precision. This study set a world record for testing Einstein's theory at a distance of just 1 millimeter, nearly the width of a pen tip. To achieve this, the researchers used an optical atomic clock, where strontium atoms are supercooled and held in a vacuum chamber by a series of lasers. These lasers create an optical lattice, a three-dimensional spatial structure made of light to hold atoms in fixed positions. Atoms in the optical lattice are excited by another laser to oscillate at a specific frequency, producing light pulses that can be used to keep. The researchers found that atoms in the top part of the optical lattice oscillate at a higher frequency than those in the bottom part, due to gravity differences. This difference is very small, only about 2 parts per billion over 1. However, thanks to sophisticated instruments and advanced analysis techniques, the researchers were able to measure this difference with an error of only about 0. This study not only demonstrates the validity of Einstein's theory at a microscopic scale but also opens up new possibilities for studying other physical. For example, optical atomic clocks could be used to detect gravitational waves, ripples in spacetime caused by the collision of massive or they could be used to search for dark matter, a mysterious type of matter that makes up most of the universe but is very difficult to detect, or they could be used to explore the connection between relativity theory and quantum mechanics. Two seemingly contradictory. Junior, one of the study's authors, said, "The most important and exciting result is that we can connect quantum physics with gravity. For example, investigating complex physics when particles are distributed at different positions in spacetime." Regarding time measurement, the study also shows there are no barriers preventing us from creating clocks 50 times more accurate than current. This is an outstanding scientific achievement, not only confirming Einstein's theory of relativity at the microscopic scale but also opening new. Simultaneously, it demonstrates humanity's progress in exploring and harnessing natural mysteries. Atomic clocks show that time is not a simple static concept, but a complex and relative phenomenon dependent on space, speed, and gravity. This is a scientific marvel, crystallized from human creativity and the aspiration to surpass limits.